has some purchase some x1 amount of this jar product and suppose x2 amount of this packet product. Okay, so suppose this man has purchased this x1 units of x1 number of jar and x2 number of packets. Okay, so here we we suppose that we suppose that person suppose purchases x1 jar and suppose x2 number of packets. The product. So in one jar, the capital A is 4 units, and B has 5 units, and C has 3 units. So if that person purchases x1 number of jar, then the A1 component 4 into x1 units, B is 5 into x1 units, and C component is 3 into x1 units. Similarly, if a person purchases this packet product, and each packet has 3 units, so if we 3 units of this chemical A, so if we purchase x2 number of packets, so this chemical A is 3 into x2 units, and B is 5 into x2 units, and C is 6 into x2 unit. And the minimum requirement of A is 8 units. So this means your constants are, what are your constants? So your constants are, this means if we you purchase x1 number of jar, so this chemical A is 4 into x1, and here this chemical, if you purchase x2 number of packet, so this chemical A is 3 into x2, and this is the minimum requirement is 8. So this means this units either equals to 8 or greater than 8, because we have to minimum requirement is 8. So this is greater or equals to 8. Similarly, for B product, B chemical, we purchase 5 into x1, because we purchase x1 number of jar, and here this chemical is 5 per unit, so packet, so this becomes x2 number of packets, so this becomes 5x2, and the minimum requirement is 15 or greater than 15. Okay. Similarly, for C chemical, this is 3x1 plus 6x2, and this is greater or equals to 16. And here we either purchase a 0 number of jar, 0 number of packet, or either in 1, 2, 3, 4, and so on. This means this x1 and x2 either 0 or greater or equals to 0. Okay, so this is your constants. This is your constant. What is your objective? Objective is the person want to spend a minimum amount of, minimum possible amount. Minimum possible amount means he have to minimize the cost this purchase. Okay, so what are the objective of this person is, objective is he have to minimizing cost, that is this means you can say you have to minimize if we purchase one jar, so this is rupees 400. So if you purchase x1 number of jar, so he spent 400 of x1 number of jar, and if you purchase x2 number of packets, and each packet has rupees 250, so this plus 250 of x2 number of packets. Okay, so you have to minimize this cost. Okay, so therefore your mathematical formulation of this problem is right as, therefore your mathematical formulation of the given problem is defined as, it's given by, okay, you have to minimize this function, and that function is you set a set. That function is 400 x1 plus 250 x2. Okay, and subject to the constants. Constants are 4x1 plus 3x2. This is beta equals to 8. This is 5x1, 5x2 greater or equals to 15. Third one, 3x1, 6x2 greater or equals to 16, and x1, x2 greater or equals to 0. So this is your problem. Okay, so here this is the objective and this is the constants. Okay, here your objective function is linear function of the decision variable, because you have to decide what amount of number of jar you have to purchase and what amount of packet you have to purchase. Okay, so this means here the decision variables are you have to decide what are the number of what are the activities. These variables are you. Is a linear function of decision variable. And subject to the condition, all these conditions are the linear equations and these inequalities. Okay, these all inequalities are linear function, and here your objective also function. That's why this problem is said to be, this problem is categorized into linear problem. This problem is belonging to linear programming problem, or in short, LPP. Okay, and you know that. How to solve this linear programming problem. So for the very first method is to solve the linear programming problem by using graphical method, and you have to, if there are only two decision variables, there are only two variables, then you can solve this in linear programming problem in a plane, and this can be solved by your usual method, that is your graphical solution of this linear programming problem. And you have to find the what are the feasible results. Okay, so you try this problem and try to solve what are the feasible solution of this problem, and where you have find the feasible region, and that feasible region is your convex cell set. Okay, so that feasible region is your convex set. Okay, so this is a very simple type of problem when this problem is your linear. And then there are certain conditions. What about for this x1, x2? There are the integer one. Then this is integral programming problem. Then if this either this objective or constants are quadratic one, then there are quadratic programming problems and so on. Okay, so here we basically in our syllabus we have already studied what are the convex set, what are the affine set, what are the convex functions and affine functions. Okay, then we move to the types of optimization problem. So in next page. So this is your basically a simple linear programming problem. Okay, so next page. So if you consider an optimization problem, for x that belongs to or before that okay, so we define what is the convex optimization problem. Okay, so before that we start with the standard form. Standard form of convex optimization problem. Okay, so here the problem is minimize any function, and that function is objective function. That's why we can write here f0 of that function, f0 of x, and subject to the constraints, subject to the constants. Here, this fix is less or equals to 0, and here suppose there are uh, I numbers of inequality sign. So suppose I equals to some finite number 1, 2. So there are m number of inequality constants and some equality constant. Equality constant means aj transpose of x that equals to ej. Okay, and here j is varies from 1 to suppose t. Okay, so if these are two types of problem, the general problem. Okay, and here this objective function f0, and your inequality constants functions means f1, f2, up to there are n number of inequality constants, so there are fn. Okay, these are convex functions, and you know that what are the convex function. Okay, so these are the convex function, and the convex function has basically three additional requirement. Okay, so what are the three additional requirement means your objective function must be convex function, and equality constants must be convex function, and your equality constants and your equality constant means this one. This one you can say this is in form of hi. Okay, so either in this form, or you can write this as we can write here hi of x. This is the inequality constant function. So h, uh, this is I, this is j. Hj of j x, this equals to uh, aj transpose x minus bj, that equals to 0. Okay, either you can write here in form of 0, in form of 0. This can be defined by hj. Okay, and here so j is varies from 1 to t. Okay, so these objective function and inequality constant functions are convex functions, and your hj of x, these are hj of x means you can write here h1 x, h2x, up to hpx. These are affine functions. These are affine functions. Okay. So if any optimization problem of type this, then your problem is belonging to convex optimization problem. And this convex optimization problem is the generalized form of any optimization problem. Okay. Suppose if your objective function is linear one and subject to the constants all are linear functions, then this problem reduces to linear programming problem. If objective function or any constants are in the quadratic form, then this problem reduces to quadratic programming. Okay, and so on. So this problem is belongings to, this is the special case, or this is the generalized case of any optimization problem. Okay, so the particular case of this convex optimization case problem has a linear programming problem, integral programming problem, quadratic problem, non-linear programming problem, and so on. Okay. So here, what are the basic property of this convex optimization problem? Okay. So an important property is that the feasible set of convex optimization problem is convex. Okay, since it is intersection of the domain of the problem, and that is the intersection of all this fi's and f0, which is a convex set with m vertex. Okay, and sublevel sets, that is x, that says that fix is less than or equals to 0, and p hyperplanes, p number of hyperplanes, because this is your affine set. Okay, so that's the, in the convex problem, the minimize a convex objective function over a convex set. Okay, so here you can write here what are the important property of this. So, um, important property. So the feasible set of convex optimization problem is convex because it is the intersection, of the domain of the problem, and that domain is defined by suppose D, and that is the intersection of collection of all I varies from 0, because this objective function is also so I 0 to m of fi, okay, and which is a convex set, which is a convex set with m sub-level sets. And this sub-level set means collection of all x such that your constant equation is fix is less or equals to 0. And there are p number of hyperplanes because this equation is your hyperplane. Okay, so and p hyperplanes, that is collection of all x such that a transpose x goes to pj. So this equation of hyperplane. Okay, so this means you can say what is the convex set, convex optimization problem. So in a convex optimization problem, in a convex optimization problem, we minimize a convex function or convex objective function, and that we have to minimize this function, and that function is convex function. We have minimized a convex objective function over a set of this feasible design is your convex set. So convex optimization function over a convex set. Okay, so this is your convex optimization problem. Similarly, you can define concave maximization problem. Okay, concave maximization problem. Concave maximization problem. So here you have to maximize objective function, that is f naught x, and subject to the constants, and constants are fix, this is less or equals to 0, where there are m number of inequality constants, so 1, 2 up to m, okay, and there are hj that equals to 0, and here the j is varies from 1 to hj is defined by a j transpose x equals to bj. Okay, this is your hj of x is equals to 0. Okay, so this problem, we refer to this problem as this is basically a concave maximization problem, and this is a convex optimization problem if the objective function f naught is concave and equality constant functions are convex. Okay, so the concave maximization problem is solved by minimizing this convex objective function minus of f0. Okay, so here your objective function, this objective function is f naught x, f naught x. This is concave. Okay, concave function, and your fix, this is the convex functions. Okay, and hj, this is affine function. If this type of problem, this problem is categorized into the concave maximization problem. And here in this problem, this is your convex optimization problem. Convex optimization problem, objective function should be convex function. This is convex function. Okay, all inequality functions that are also convex functions, and your equality functions, that is affine. Okay, so this type is belongs to convex optimization problem, and this type of problem is belonging to concave maximization problem. And you have to reduce this concave maximization problem to convex minimization problem. Okay, so convex minimization problem by using the objective function is you have to take this objective function to minus of f0. Okay, so this problem is reduces to convex minimization problem by using, you can write this is minimize of minus of objective f naught x. This problem reduces to convex minimization problem. Okay, so now okay, so if we take any function and try to see that function is convex or not in the given domain, because you have to check your problem is convex optimization problem or not. So that's why you have to check that that function is convex or not. Okay, so next page. Okay, so suppose that any function take simply x1 to x2. You have to check this f, this function. So is this f convex over set C, and that C is collection of all x, so that x1 is greater or equals to 0 and x2 is greater or equals to 0. So you have to check this x1 into x2. This is convex or not. So you have to check this function is convex or not. So here, first of all, we solve by our usual trick. Okay, and that we know that if we take any point which is belonging to that set C, and if we are able to find take 2 points, okay, which is belonging to that set, and if we take the convex combination of these 2 points is also belongs to that, that means the set is convex. And if the functional form, the image of that is belongs to greater than that, this means your function is not convex. Okay, so this means you have to, if we take any 2 points, suppose if we take any 2 vectors, suppose if we take any vector x and second vector is 2 points, suppose if we take any vector y. Okay, so y has component x1 and x2. Okay, so if we take some point which is both components are greater or equal to 0, so we take suppose 2 point. Okay, 1 point of that C, and suppose another point if we denoted by y here, So this point is supposed to take to 1 point. Okay, because here both entries of x1 and both x1 and x2, x1 and x2 both entries are greater or equal to 0. So we take this 2 point and this x1 xy points belonging to your set C. Okay, so if we are able to show that the honest combination of these 2 points and image of that, okay, so we have to find the image of this image of, because we have to check this set is convex or not. हमें ये check नहीं करना, हमें check करना this function is convex or not, and that function defined by that these two. Okay, this if we take the convex combination of these 2 points, this means if we take theta of x and plus 1 minus theta of y, and the image of this means this is your function, and image of this means there's a graph of function. If the image of this function is, if you take any 2 points, the image of this is always less or equals to if we line joining that 2 points. This means this function is important. So this means you have to prove that this is less or equals to the image of that point, because this, if this point is x, the image of that point is fx. If this is y, so this is fy. If we take the line straight line, so theta of this plus 1 minus theta of fy. If you are able to prove that this thing, so your function, so this implies if this satisfies, then f is convex. Okay, so if this satisfies, then this is convex function. This is convex function. So here we take any random x and y points. Okay, is this, and then we are trying to find what are the value of this convex combination of these 2 points. So then theta of x plus 1 minus theta of y. What are the value of this? So here we know that this x component are 1 and 2. This means theta, and x is 1 and 2 component, and plus 1 minus theta. What are the y component is 2 1. Y component is 2 1. And if we try to solve this, this is theta plus 2 minus 2 theta. So this becomes 2 minus theta. And here 2 theta and plus 1 minus theta. This becomes 1 plus theta. Okay, so this is theta of that. Okay, so you have to find the image of that function. So hence f of this theta x plus 1 minus theta of y. So this is simply f of, and what is the value of this? This value is 2 minus theta and 1 plus theta. Okay, so what are the function value? X has component x1 and x2. So this product of x1 and x2. So this means this equals to this 2 minus theta into 1 plus theta. 2 minus theta into 1 plus theta, and this equals to 2 plus theta minus theta square. Okay, then we have to find this thing, theta into fx and 1 minus theta into fy. Okay. So here, what's the value of this theta of fx and plus 1 minus theta of fy? This equals to theta. What are the fx? Fx means this thing, f of 1 2, and 1 minus theta fy. Fy means this is 2 1. Okay, this equals to theta. f12 means it is product of 1 into 2 and plus 1 minus theta, and the product of 2 into 1. Okay, so if you're solving this, this becomes 2 theta minus plus 1 minus theta into 2 theta. So this equals to only 2. Okay, so here this means you have this point. This is suppose equation star, and this is beta star. Okay, so you have to take any value of theta. Okay, so if for example, if we take any value of theta, and that theta is supposed to take simple half. Okay, suppose the midpoint of that. If you find this theta equals to half, your theta is 1 2. Okay. So theta is half, and that is belongs to closed interval 0 1. Okay, so then you have to find what is the value of this star. Okay, so then you f of, if we try to find theta is equals to half, so this becomes half of x plus half of y is equals to 2 plus half minus 1 by 2 square, and this equals to 9 by 4. Okay, and here uh, this is from star. Okay, and from equation double star for theta equals to half, so you find this half of fx plus half of fy, this equals to 2. Okay, so you see that this is something greater than this because this equals to 2.25. Okay, and this is 2. This one is greater than. So this implies for theta that equals to half, which is belonging to 0, 1, you get this value as f of this theta x plus 1 minus theta of y. This value is 9 by 4. This is greater than that value, that is uh, theta of fx plus 1 minus theta of fy. So this condition doesn't hold. This condition doesn't hold. Or you can say that this implies f of theta x plus 1 minus theta y. Okay, this image of this is not less or equals to theta of fx plus 1 minus theta of fy. So this implies fy for theta belonging to 0, 1. Okay, so this implies f is not convex. Okay, so this means f is not your convex function. तो इस तरह से आप इजीली चेक कर सकते हो कि फंक्शन इज कॉन्वेक्स और नॉट over the set, this set C. Okay, so you have to calculate this is convex or not over that set C. Okay, so similarly, if we take another example and try to see that is convex or not. So okay, so here we have to define a simple quadratic form. So next page, so we have a theorem for all quadratic form. Okay, तो quadratic form के लिए हमारे पास एक theorem है, तो हम डायरेक्ट वहीं से चेक कर लेंगे. So we have a theorem, quadratic form suppose f, which is from Rn to R, and this quadratic form is given by, you know that this is a quadratic form defined by the matrix form you can write here, where this matrix Q be the symmetric matrix. Okay, so here what are the Q? Q be the symmetric matrix of order n. Okay, and this is symmetric, so Q equals to Q transpose. So this is convex. This function, this quadratic form, is always convex on set C, if and only if and only if for all xy we take 2 points which is belonging to that set C. Hello. Okay. For all xy belongs to C, this x minus y transpose Q x minus y, if this is positive semi-definite. Okay, So this condition holds, then your function is always convex. Okay. So here we can prove this by using A. So here, the proof of this theorem, we have already proved that type of theorem already. Okay, okay. तो एक थ्योरम तो हमने इसको किया ही था, तो इसको आप खुद से ट्राई करिए, बिल्कुल क्वाड्रेटिक फॉर्म के लिए हमने किया है, बिल्कुल वैसा ही है, तो आप इसे खुद से करने की कोशिश करें। और okay, and here if we take some example, if we take some example here, and okay, so अगर हम पिछला ही प्रॉब्लम लें, and for this function fx that equals to x1 and x2, okay, x1 and x2, so this x1 and x2, and you have to check this function is convex or not, okay, this is convex or not. Previous example आपने लिया x1 x2 लिया आपने, okay, and this x1 x2, this function can be written in matrix form. So you can written as this function fx equals to x1 x2, and this is written as a functional form, that is x transpose qx, okay, and here what is the value of q? So here q is 1 by 2, and this is 0 1 1 0, okay, so you can write this quadratic form in this form, okay, and here your C is here you basically your set C. So defined on that set C. C is the collection of all x such that x is greater or equals to 0. Okay, so this is your set C. Okay, so here we take x and y, two elements here. Okay, so here we take suppose let x, okay, x component, suppose 2 2, where two components are greater or equals to 0. So with x we take 2 2, and suppose y if take any positive number, say 1 3. Okay, this is, and these two are belongs to C. Okay, because C is the collection of all x such that your x1 is greater than 0 and x2 component is also greater than 0. Okay, so this is your just previous value. So here, by using this theorem, you can find out what is the value of this is x minus y transpose q x minus y, or in some book you can find y minus x transpose, because you take two vectors, so either this minus this or y minus x. Okay, so either this form or this form. Okay, so no problem here. Okay, this is set of to 0. Okay, so here if we take this y minus x transpose and q y minus x, we have to find what is the value. Okay, so here this is 1 by 2 because q equals to half. Here y minus x transpose, so this means minus 1. If we this minus this, and 3 minus 2 is 1 1. Okay, this is row vector because transpose q is 0 1 1 0. And what is y minus x? Y minus x is minus 1 and 1. Okay, so if we try to solve this, this becomes minus 1, which is less than 0. This is less than 0, and if this is greater or equals to 0, then your function is convex. So this is less than 0. So this implies hence f is not convex, on set C. Okay, so here you can easily check that with previous problem. By this theorem, you can easily check that this is your not convex function. Okay, तो इसकी प्रूफ कैसे करेंगे? प्रूफ के लिए हम बता दे रहे हैं, आप बिल्कुल सेम हमने करा भी रखा है. So here the function fx is x transpose qx is convex even if for every theta which belongs to 0 1 and every xy that belongs to Rn. So we have this f of this form. If you are able to prove that this is the convex, this means uh, okay. So if your function is this proof of that, proof the function uh, is fx, that is x transpose qx, is convex if and only if and only if for every theta, for every theta that belongs to 0, 1, 0, 1, and every xy that belongs to Rn. So we have, we know that the formula is the image of the convex combination of these 2 points, 1 minus theta of y, is always less or equals to the image of the convex combination of the image of that point x and y. Okay, so this means you can say this can be written as theta of fx plus 1 minus theta of fy minus of f of theta x plus 1 minus theta of y. This is greater or equal to 0 if we this transform this side to this side. Okay, and this form is already we did in last class, where the quadratic form we have to prove that that is a convex. This is always greater or equal to 0 when your matrix is positive semi-definite. Okay, so similarly here you can solve this by using theta, and what is our fx? Fx is defined by this formula, x transpose of qx. Okay, so this is fx. And here 1 minus theta into what is fy? Fy is y transpose q of y minus here f of this means is theta x plus 1 minus theta of y transpose q, and this is theta x plus 1 minus theta of y. Okay, this is greater or equal to 0. So you have to prove that this thing. Okay, so here you solve this, and finally you get this is convex if and only if you can solve this x minus y transpose q of x minus y is greater or equals to 0 when q is the positive semi-definite. Okay. So this is this condition holds. Okay. So here no condition on that your q. Okay. So if this condition holds, then your function is convex. In last theorem, we have proved that if this q, if q is positive semi-definite, then your function quadratic form is convex. And here, no condition on that q. Okay, so here you can find this inequality reduces to this. Okay, कैसे करेंगे? ये बिल्कुल सेम स्टेप्स हैं जो हमने लास्ट क्लास में उसमें क्वाड्रेटिक फॉर्म के लिए कराया है, बिल्कुल वैसे ही आपको करना है. Okay, suppose if next page and we take some examples. For example, here you have to determine whether the following functions are convex, or concave, or neither convex nor concave. Okay, and the problem is there are three problems. Okay, the problem first is, so mapping is from, we take R to R, and the function is minus of 8x squared. Okay, and so the second is If we take R2 to R, and the function is equals to x1 x2 minus x1 square minus x2 square.
So first question fx equal to minus 8x square.
Minus 8 s square. 8
Okay.
square. And third one is mapping from R3 to R, and the function is R3 means x1 x2 x3. So this is 4 x1 square 3 x2 square plus 5 x3 square plus 6 x1 x2 plus x1 x2 x3 minus 3x1 minus 2x2 plus 15. Okay, so this type of problem here. First problem is simple R2R. Second one is there are x1 and x2, two variables, and third one is x1, x2, x3. And suppose if we take Rn x1, x2 to the xn. Okay, so this type of problem. So in first we compute basically we have to find the Hessian in this case, and just for the first case here, we have to find the matrix means quadratic form. Quadratic form आपकी क्या होनी चाहिए? If quadratic form, if quadratic form is uh, positive definite, positive definite, then function is convex. Okay. So for that, you have to finding the Hessian matrix. Okay. You have to find the Hessian. Here, for single variable, the Hessian means only the second derivative. So here, your second derivative is what is d2f over dx square. So this is equals to minus 16, which is less than 0. Okay, so for all x which belongs to R, for any x, for all x that belongs to R, so hence your f is concave here, concave, because this is not greater than 0, greater or equals to 0. So this why first one is your concave function. What about second? If we take second one, the Hessian matrix of the Hessian matrix of this f is will be noted by capital X is equals to del 2 f over del x 1, okay, square, and the Hessian matrix of this equals to if we take the second order derivative of this with respect to x1, this becomes minus 2, and here x1 x2 this becomes 2, here x1 x2 this becomes 2, here x2 del 2 f over x2 square this becomes minus 2. Okay. This is your Hessian matrix. So here we know that the principal minus, so this is the first principal minus. Okay, so this is your delta 1, this is delta 1 is minus 2. What about delta 2? Delta 2 is the determinant of minus 2 to 2 minus 2. This thing, okay, the product is 4 minus 4. Okay, this equals to 0. This equals to 0. This means your delta 1 is less than 0, delta 2 equals to 0, which is, this means, which is negative semi-definite. Negative semi-definite, because this first minor is the delta is less or equals to 0. Delta is less than 0, the equals to 0, less or equals to 0. This is negative semi-definite for all x that belongs to R2. Therefore, your f is concave in whole R2. Okay, and now for the third one, here we find the Hessian matrix of f. So here The Hessian matrix of this f is defined by this fx. This equals to del 2 over x1 square. X1 square means this is 4 times, and then x1 x2. So x1 x2 this is 6. You write this 6, and then x1 x3 this becomes 1. Here x2 x1 x2 x1 again 6. Then x2 square is 6. Then x2 x3. So no component is x2 x3. This becomes 0. So 3 1 x1 this becomes 1. 2 3 is same. 3 square this is 10. This is 10. Okay. This is your Hessian matrix. Then you find all principal minus, that is this is delta 1. So this first one is delta 1. Delta 1 equals to 8, but is greater than 0. What about delta 2? Delta 2 is the second order. This one is delta 2. This is 8 6 6 6. 48 minus 36, that is 12. This is also greater than 0. What about delta 3? This is of 3 cos 3. This one. So you have 8 6 1 6 6 0 1 0 10. And you find the determinant of that, and that is equals to 1 1 4. This is also greater than 0. Okay, so this means all this delta 1, delta 2, delta 3 greater than 0. So you write here your fx is positive, definite, positive, not semi-definite, because any one is not equal to 0 here. Positive definite. Positive definite means this function f is strictly convex. Strictly convex. Okay. If anyone is equal to 0, then you find the positive semi-definite, and that's why your function is convex. So here you can find easily this is your function is a convex function over R3. ओके, तो इस तरह से आप कर सकते हैं। फिर नेक्स्ट टर्न पे हम कुछ और कुछ थ्योरम्स भी हैं, थ्योरम्स भी कराएंगे, फिर न्यूमेरिकल भी कराएंगे। ओके, तो आज के लिए इतना ही करते हैं। थैंक यू।
Thank you, sir.
Thank you, sir.
Thank you, sir.